Very good morning to all of you. All are joining. Please join fast. Today we will take the session of RFS lab. So have you completed the file work of RFS? Please submit your files till first 3 experiments. Yes. Okay. Very good. So waiting for 2 more minutes so that maximum students can join the lab. After this lab, you will be having the class of Abha ma'am, I think.
Hello, this is Kyle Davidson, and today I'm going to give...
Okay. I'm taking the attendance. Write your roll numbers in the chat box, Aditi. Amisha, Avantika, Shubham. Shubham, you haven't attended any of the lab session of RFS? Which lab you attended? एक भी लैब में प्रेजेंट नहीं है तुम्हारी. डीएसपी लैब तुमने अटेंड की थी, आरएफएस अटेंड नहीं की है. So we will start with the next experiment. I'm sharing my screen. Is it visible? Screen is visible, students? So you can try it on your HFS software. Okay, we will start with the second experiment. What we have to do in first experiment, we have studied basics of HFS software in three labs. Then we studied the first experiment, that is rectangular waveguide designing. In similar way, now we have to design a circular waveguide. By the nature, we know how your rectangular waveguide is there and what is the difference between circular and rectangular waveguide. By the shape we can define, and by the radiation pattern we can find out the difference in between circular and rectangular waveguide. So here what we have to do, design a circular waveguide having a cutoff frequency. You can take any of the cutoff frequency. This is one of the example. We are taking this much of cutoff frequency, and that is also based on the radius of the circular structure. So it's just like a transmission line we design. It is circular in shape. So to design transmission line, first we will design circular waveguides. So we are taking cutoff frequency of 879 megahertz and we are working in TE11 mode. You can work in other modes also. Okay, but I am specifically designing this at TE11 mode. So M and N both are 1. And observe the field patterns of horizontal and vertical orientation of for TE11 mode inside the circular waveguide. We have seen rectangular waveguide, how the wave propagates, what is the electric field, where the intensity lies maximum, where the intensity is minimum. We have seen its vector field, we have seen its magnitude. See, till this lab hasn't started, you have just seen all these things theoretically. In the books you have seen the diagram, you saw that the wave propagates upward in upward direction, it propagates in downward direction, but here in this you can visualize, you can analyze, you can have a 3D view of all the things happening within the waveguides. You can see the current flow, voltage, magnitude, vector, what is the intensity of magnetic field, electric field. You can see all these things here. Okay, so which software we are using? We are using HFSS software. So what is a circular waveguide? Circular waveguide consists of a hollow metallic cylinder. We all know what is the shape of circular waveguides. It is a hollow metallic cylinder with an inner radius capital R as shown in figure 1.3. In the inner air field volume of the cylinder, electromagnetic waves can propagate. Above mode specific cutoff frequencies, the wave will propagate above the cutoff frequencies. Solutions of Maxwell's equation can be found using cylindrical coordinate system. You have studied electromagnetic field theory. There you have studied Maxwell's equation for both Cartesian coordinate and cylindrical coordinate system. So here we have to use all the Bessel functions and cylindrical coordinate system functions to find how the wave propagates in the circular waveguide. Okay, so solutions of Maxwell's equations can be used to find cylindrical coordinates and involve Bessel functions. As in the case of a rectangular waveguide, the solution can be divided into TE and TM modes. We all know transverse electric and transverse magnetic modes. We can find out the solutions in both the modes. The different modes are identified by the integer numbers M and N. Okay, so M is 1, N is 0, so it is 1 0 mode. If M is 0, N is 1, that is 0 1 mode, which is the fundamental mode of the system. Is it audible to all? Okay, few more students have joined. Okay. So we can see the designing is same. The outputs are similar as your rectangular waveguide. The same way we have to follow, but just the formulas are changed a little bit as it's a circular in shape and that was rectangular in shape. So this figure you can see circular waveguide, x, y, z, 3 coordinate system, diameter is equal to 2r. Diameter is equal to 2r. You can see that. And epsilon is taken as 1 epsilon 0, dielectric constant. The wave mode with the lowest cutoff frequency is known as a fundamental mode. Clear? But here for circular waveguide, the fundamental cutoff mode is TE11 mode. For this fundamental mode, we are designing this circular waveguide. You can design this for other modes also. ठीक है, but we are starting with the basic mode, that is the fundamental mode, or which is having the lowest cutoff frequency. So that is for M and N1. The electric field distribution in a cross section area is shown in figure 1.4. Next figure you will see the cross section area of this. Since the cross section is a circle, there is no preferential direction for the orientation of the electric field, as it is in circular design, so we can't identify the orientation of electric field. We can see a vertical field orientation and a horizontal field orientation. You can see this in the diagram. In practical operation, the orientation depends on the excitation of the mode. We can use orthogonal polarized waves of the fundamental wave mode to transmit two independent data streams simultaneously. Circular waveguide component is shown in figure 1.5. So you can see this diagram. You can prepare your lab copies. In that you can write the heading, figures you can draw, whatever instructions I am giving in the lab sessions, online lab sessions, you can write those things in your copy. See, as soon as college will start, if practical classes will be there, your lab exam will be there, then you have to submit your practical lab copy, whatever instructions I am giving, that you have to write in your lab copies. And experiments you are submitting online. Okay, that hard copy you have to maintain, and whenever the college will start, you have to submit all those documents. So you can see the field orientation for TE11. Circular waveguide could be in both the directions. As your waveguide moves, your direction of propagation will change. Since the cross section is a circle, there is no preferential direction for the orientation of electric field. We can see a vertical field orientation and a horizontal field orientation for TE11 mode. Clear? This is a circular waveguide component. You can see it. Then we will talk about the cutoff frequencies. At what cutoff frequency the wave will propagate. Okay, as it is the lowest cutoff fundamental mode. So how we will define? We have defined cutoff frequency in previous experiment also, rectangular waveguide. Depending on that, we have decided the dimensions also for rectangular waveguide. Okay, so cutoff frequency. Similarly, as in the case of rectangular waveguides, propagation in circular waveguides is determined by a cutoff frequency. The cutoff frequency is unique for a particular waveguide mode that is supposed to be propagating in a waveguide of a given diameter and determines the lower frequency of the waveguides. Operating frequency range. The cutoff frequency for circular waveguide is calculated using the following formulae. So, of a given diameter determines the lower frequency of the waveguide's operating frequency range. So, the cutoff frequency is given by Fc m comma n nu upon 2 pi Bc. What is nu? Stands for the wave velocity in a medium filling the waveguide. It's a frequency only. Wave velocity in a medium filling the waveguide. What is beta c? Is a cutoff phase constant, beta c, which is calculated according to the formula given in the table. This table will help you to find out the value of phase constant. Cutoff phase constant formula for circular waveguide modes. TE modes and TM mode, transverse electric and transverse magnetic mode. So beta C is very important parameter, as it tells you about the cutoff phase constant on which your cutoff frequency depends. Fc is equal to nu upon 2 pi beta c. Beta c is the phase constant. C आ गया है, that means it is a cutoff value. After this cutoff value, your wave starts propagating through the circular waveguide. So propagation of wave in circular waveguide is determined by this cutoff frequency. And what is this phase constant beta c? It is given by xi dash mn upon a. What is this xi x? It is the nth root of the mth Bessel function. Dash आ जाता है means it is the nth root of the mth Bessel function derivative. So here it's the first order derivative. For transverse magnetic mode it is direct the Bessel function. Bessel function find करोगे directly लिखोगे तो that is used for transverse magnetic mode. Xi dash is used for transverse electric mode. A is the radius of the circular waveguide, which is the most important parameter because here you have to define the radius due to which on which your cutoff frequency depends. Okay, other parameters, the length is not important. You can have any length of the circular waveguide. So now this formula should be written in your copy. Okay, so now for TE11 mode, if we take the radius of a waveguide as 10 centimeter, you can take radius as different values, 7 centimeter also you can take, but all these calculations are needed to be done because xi value is not known to us. We have to find the standard value. It is having a standard value. This standard value is given in standard books. So while designing any circular waveguide, if you want to design or you want to change the radius, then for that particular radius, we have to find the value of beta c first. For that beta c, I should know the value of Bessel function. So these standard values are given in the standard books of microwave engineering. So from that book, you can find out these values, or it is also available in the net. You can put on the Google, you will get these values. So for A is equal to 10 centimeter, the cutoff frequency comes out to be 879 megahertz. Okay, that's why I have written in the aim that we are having a cutoff frequency of 879 megahertz. Okay, you can see I have mentioned here having a I am designing a circular waveguide with a cutoff frequency of 879 megahertz. Clear? You can design for other values also. So values of Bessel functions are calculated. Okay, who is joining? And Sakshi. So is it clear? See, just you practice on HFSS software, and if you are unable, see the videos because I am not sure whether so they are designing it for a 10 centimeter. You can design for other values also. Okay, this is the inner diameter of your circular waveguide. Clear? So Fc is equal to, I am substituting the value of beta as xi upon A. So this is my formula for 1, 1. M and N value I am taking as 1, 1. And this value comes out to be, this Bessel function, derivative of Bessel function comes out to be 1.841, which is a standard value. No need to calculate. You can directly use this value. So Fc, the cutoff frequency for this circular waveguide with radius 10 centimeter or 0.1 mm is coming out to be 879 megahertz. C upon 2 pi 1.841 upon A. C is the, what is C? What is A? Please write the answer in the chat box. C की value क्या होती है? What is the value of C? Please be active and be attentive in the class. C is the speed of light. What is its formula? 3 into 10 to the power 8. Yes, what happened? Aditi, Avantika, not attentive in the class. Shubham, Priyanka, is it audible? Any problem? There is a problem? Okay. So please respond. We are taking just 20-25 minutes lab sessions. So please be attentive. Okay. So we got this value of FC. Waveguide design on HFSS. A is the radius, that is 10 centimeter. D is equal to length. Length of waveguide is any multiple of wavelength for TE11 mode. Here we are taking it equal to the wavelength, that is about 34 centimeter. Lambda से equal ले रहे हैं हम, that is 34 centimeter. Mode is TE11 mode. Okay. So now we will start designing. Okay, what is the procedure? Procedure is to first select, open the HFSS software, choose a driven model, then draw a cylinder on HFSS having center position 0, 0, 0 and radius 10 centimeter and height 34 centimeter. Select the faces excluding the waveport faces of the circular waveguide and assign the boundary finite conductivity to all surfaces. Boundary conditions are needed to be applied. जैसे हमने apply की थी पहले भी वैसे ही मुझे apply करनी है rectangular waveguide में. So here I will choose the boundary of finite conductivity to all the surfaces. Assign the wave port on the two port faces and define two modes for each port. Create the solution setup. Create the solution setup. Set solution frequency, add frequency sweep. Same steps which you followed earlier. We have to analyze that only. Validate the design and further analyze it. Observe the field patterns for TE11 modes in the port field display. So these steps are important when we are designing. Okay, and you should remember these steps. These steps are fixed only. कि एक के बाद एक हमें सेकेंड नेक्स्ट स्टेप क्या करना है. ठीक है. Observe the field pattern for TE11 modes in the port field display option in project manager. Plot the corresponding E and H field patterns. Okay. So these steps you have to follow. If you are using your computer or laptop, whatever you are having, you open your HFSS software, start designing it, follow these steps, and I am there to help you out while designing. Clear? So after following this process, I will get a cylindrical waveguide structure. I will get a cylindrical waveguide structure. Is it okay? This designing waveguide structure, and we can see the results also. In this way, you will get the electric field intensity maximum at the center, intensity reduce outside. This you can see the field pattern, E field pattern, H field pattern in circular direction. This is going outwards, electric field going outwards. This is rotating in between the your circular waveguide. So any doubt you want to ask? Any doubt you want to ask? No doubt. So we will see this experiment by performing it. We will continue this lab. So I think there is no doubt. Okay. So goodbye, students. Complete your experiment.